We're going to close out our practice with probability. Now we're going to look at two famous probability questions, the birthday problem and the Monty Hall problem. All right, so here's the birthday problem in one form. Suppose you're in a classroom with a total of 40 students. What's the probability that at least 2 students share a birthday? Now, to simplify this problem, for our example, we're going to assume 2 things. We're going to assume no one was born on February 29th, and we're going to assume birthdays are uniformly distributed throughout the year. So we have equally likely outcomes for people's birthdays. So take a minute and see how you would set this up. First hint is if I want at least 2 students, in my head I start saying, well, I need 2 students, then I need 3 students, then I need 4 students, or I need a pair. There's just so many options, right? I could have 2 pairs of 2 students who share a birthday. I could have 3 pairs of students who share different birthdays. Already, that's just a lot of things to add up together, which is making me think the complement rule is probably going to be my friend. And so that's how we're going to start. First, we're going to think it's much easier to calculate the probability of no shared birthdays in a group of 40 people. And then I can go to think, all right, well, I asked the first person, what's your birthday, right? And I then calculate what's the probability that person has a unique birthday. Well, that's definitely a probability of 1. The first person I choose, so that's a unique birthday. Then I'll say, okay, what's the probability the second person I choose has a unique birthday from the first person I chose? So what's probability that B2 is unique given that I have a B1 birthday already chosen? That's going to be 364 out of 365. And then for the third person to be unique, I have 363 out of 365. So I keep multiplying these together, and you can notice my denominator will be 365 to the number of students, so in this case, 40. And then my numerator is actually going to be 365 factorial. I'm going to be going all the way down, but then I'm going to stop here at 365 minus 40 factorial. If I put that in the denominator, I will stop at exactly the right numerator value. That is the probability of no shared birthdays. And so I want the complement of that. So I want 1 minus that. And I basically have almost a 90% chance of at least 2 shared birthdays. Fun fact about this is you can generalize it. I think you can start to see the pattern here that once you pick the number of students or the number of people in the room, you change that 40 just to an n. And so if we do that, this is the probability of at least 2 people out of n people sharing a birthday. And this is a plot. This is just the plot of the no shared birthday. So just this part here, not the 1 minus. And so we can see that as soon as you have a group of 23 people, that's going to hit the cutoff right here at 50%. Then there's a 50% probability at least 2 of them will share a birthday. And as soon as you get above 23 people, you can see this is the probability of no shared birthdays. So as I get above 23 people, this probability of no shared goes down and down and down. And therefore, the probability at least 2 of them share a birthday increases. So that's a fun party game you can play. And the odds are in your favor as soon as you're in a room with at least 23 people. Let's look at one more famous probability problem that was actually inspired from an old game show called Let's Make a Deal. The way this game worked is behind one door was a prize. It was random which door it was behind, equally likely to be behind any of the doors. Behind the other 2 doors was nothing. And so the contestant was asked to choose one of the 3 doors. Then the host opened one of the other doors and showed it was empty. Or I think at the time they did this, they put goats behind the non-prize doors. Then the host asked, would the contestant like to switch to the other unopened door? The question is, should you switch? From a probabilistic standpoint, do you have any advantage in switching, or does it not make a difference? So mathematically, I'm asking, okay, we know that if I just randomly choose a door, I have a 1 in 3 chance of winning. What is the probability of winning given that I switch? Knowing that there's this extra information and knowing that the host does know which door the prize is behind, and so the host is always going to open a door that has nothing behind it. Okay, so take a minute, try to see if you can calculate and compare these probabilities. All right, I'm going to do this first visually, and then we'll look at it through formulas. But a visual way to think of it is, let's say you chose door 1. There's a 1 in 3 chance that you're correct, 2/3 chance that you're wrong. But then the host is going to open one of these other 2 doors that you didn't choose, and they're only going to open one of these doors that doesn't have a prize behind it. So for example, I'm just showing the goat here. Well, the chance that your original door was correctly has the prize is still 1/3. Nothing changed there. But what did change now is that 2/3 chance here really just got shifted because you were given extra info and you know that this is no longer a door that has a prize. So when you think of it this way, since you only had a 1 in 3 chance of correctly guessing, and now that the host narrows down your options, this door has a 2/3 chance of actually having the prize behind it. So you're better off if you switch. Let me show it to you another way. Again, without loss of generality, let's say you pick door A or the first door. Again, there's a 1/3 chance that the prize is actually behind each given door. So let's go down each of these scenarios. Let's suppose you chose door A and the prize is actually behind door A. Let's look at what happens if you switch. So probability that you win, given that A had the prize, you picked A, and that you switch is 0. So that's a scenario where you should have stayed. Okay, now let's look at the scenario. Again, you pick A, but the prize is behind B. So in this case, the host is going to have to open C because they won't open the one where the actual prize is. And you're going to switch to B and you're going to win. And last option is the prize is behind door C. That means the host will have to open door B. If you switch, again, you'll win. And so now using the law of total probability, putting all of this together, this means I'm going to get a 2/3 chance. Probability that I win, given that I picked A and I switch, is going to be 2/3. So from a probabilistic standpoint, you actually should switch. Now, this problem is not intuitive to most people. And so I'm going to show it to you in a way that may make it a little more intuitive if we extend this idea to, instead of 3 doors, think of 100 doors, okay? And so again, you get to randomly choose one of these doors that has a prize. So let's say I choose this one. Now the host knows where the prize is. They're going to open every other door except the one where a prize is. So they're going to open these 98 other doors. They're going to leave 37 closed. And now the question is, should you switch, right? So we know now that the prize is either behind 37 or it's behind 1. Now, there was really only a 1 in 100 chance that this random door you chose first actually had the prize behind it. The host knowingly opened every other door except 1, 37. So there's actually a 99 out of 100 chance that the prize is behind door 37. And yes, you should switch. Fun history fact about this problem. In as late as the 1990s, this was asked by a reader in Parade magazine to columnist Marilyn Vosavant, who actually answered a bunch of different questions that readers would write in. They asked this Monty Hall question. She correctly answered that you should switch. And in the following months, she received more than 10,000 letters of people telling her that she was completely incompetent. Here are some snapshots and some quotes of people that were responding to her at the time. And these were not just, random people that didn't understand probability or statistics. These were people that had a lot of education in it, and even then were struggling to understand this. And so this is just to give you some consolation. If you're finding probability not the easiest and not the most intuitive. You're not alone. The human brain has a hard time thinking probabilistically and statistically without practice. And so this is really something where the more you practice, the better you'll get at this. And yes, you're not alone. And fortunately, people conceded when they realized they were wrong and Marilyn was correct. But this is an example of even how not so long ago this problem was still causing problems for people and challenging people's understanding. All right, so keep up the good work and keep up the practice.